quite a bit of terms related to acidity, and we also introduced free energy relationships. So I just want to start by wrapping that up and doing or showing you the direct relationship between free energy and acidity. So okay, so there are many different ways to express delta G. One that is most commonly used is minus RT natural log of KEQ. And R being the universal gas constant, T is temperature, and remember that that is in Kelvin as opposed to Celsius. And we can show that, you know, I've told you in the past lectures, the more negative the pKa, the more acidic. We can see that from this equation, how it relates to free energy. So I'm going to bring back two acids that we're now familiar with. Okay, so the top one is acetic acid, the bottom one is then trifluoroacetic acid. And one can measure the equilibrium constants for this reaction. So okay, for acetic acid, the KEQ is about 1.73 by 10 to the minus 5. So this exists very far to the left. In other words, acetic acid doesn't undergo very much spontaneous ionization in water at room temperature. If you look at the trifluoroacetic acid, the KEQ for that is about, where is it here, 0.588. Okay. And so this reaction proceeds much further to the right, although it still favors the unionized acid. So I can take this and basically plug these two numbers into the equation above, into this delta G relationship. And if you do that calculation, I'm just going to make a table over here. If you do that calculation, you get a change in free energy of about 6.67 kcals per mole. For acetic acid, and 0.32 for trifluoroacetic acid. Okay, so what does this tell me? It tells me that in the ionization of acetic acid, the energy of the system is increasing. It's a higher energy state. Delta G is positive. Okay. When I ionize trifluoroacetic acid, the free energy of the system still increases, but by significantly less than what we would expect or by significantly less than acetic acid. And so there's much less energy input required to ionize trifluoroacetic acid. Therefore, it is a stronger acid. Okay. And remember that pKa is just minus log KEQ. And so if I do that, I get to 4.76 and 0.23. 0.23. Okay. Okay. And so just write it one more time to drive home the point. The more negative the pKa, the stronger the acid. Okay. So, so this is the direct relationship between pKa and free energy, and the positive increase in free energy, because you have the negative sign in the conversion to pKa, leads to a higher energy or higher value for the pKa. As my free energy approaches 0 and then goes negative, my pKa gets smaller and smaller and ultimately can enter negative regimes. Okay, and so these are important equations to remember. They help you to relate free energy to acidity. Okay. All right, so that's all I want to say about that. I want to start talking about alkenes, and we're going to introduce the bonding and the line diagrams, and then we'll talk about, we'll build a molecular orbital diagram for alkenes. And so they're basically anything that has a CC double bond. Okay, and we typically can draw them like this. If you like, you can draw the Lewis dot structure, which would be one with 4 electrons between the 2 carbons. Okay, and then the sort of ultimate, the maximally simplified diagram is just not to even show the carbons explicitly, just to put a vertex. Okay, and so this 2 carbon alkene is a special name. This is ethylene. And I think they spray it on tomatoes to make them ripen once they get to the store. We'll talk about the bonding. So we can first apply the Vesper model to think about the geometry. And so each carbon has 3 things attached to it. And so these are going to be trigonal. And the bond angles are approximately 120. So okay, they're not perfectly 120 degrees because you've got hydrogens and a carbon attached to a carbon, so there's some variation, but they're approaching 120. Okay, and then we need to think about the bonding. All right, and there are questions here that you haven't seen before. And the first thing that we have to take note of is that there are 2 distinct types of bonds in ethylene. Okay, there are, of course, the CH bonds, which are sigma, and then the CC single bond, the first CC bond, is also a sigma bond. Why is my pen? Okay, But there's a new type of bond that we haven't seen yet, which is the pi bond. Okay, so the second bond between the carbon atoms is of a different type. And we call that a pi bond, okay? And so sigma bond had a specific definition, cylindrically symmetrical with respect to the bonding axis, okay? Pi bonds also have a specific but different definition, and that is that there is a nodal plane along the bonding axis. So okay. And so once we know the types of bonds, we can then start to think about the hybridization of the carbon atom. Okay. And I've got 3 types of sigma bonds on each carbon atom, 2 to H and 1 to carbon. And so what I want to do is have hybrid orbitals that are identical for each of those atoms that the carbon can donate. And so what we say is that the carbon, we form hybrid orbitals from 1 s orbital and 2 of the 2p orbitals on carbon, okay? And so number of AOs in equals number of hybrid orbitals out. So 3 orbitals in gives me 3 hybrid orbitals. And so we say that the carbons then are sp2 hybridized. Okay, so I combine 1 2s, 2 2p's, and I get out 3 sp2 orbitals. Okay, and so we can draw this schematically, and then we'll construct a bonding diagram. And so hopefully between the 2 representations, the bonding will be apparent to you. Okay. And so I'm going to draw my carbons. I'm going to make this big so it's easy to see. Draw my carbons with their bonding axis like that. And we said that the atoms are trigonal, so they're flat. And so I'm going to look at this thing from the side. And that means that I've got a hydrogen coming out here and a hydrogen coming out here. And then a hydrogen going back. And then another one going back, okay? So it's as if I've got that plane defined by the carbons and the hydrogens perpendicular to your screen, okay? And we're looking at it from the side, right? And so each of these, I've only drawn the sigma bond, and each sigma bond is comprised of an sp2 orbital. So And I'm just going to draw it for carbon because it's going to get very busy if I try to draw everything in. Okay, and so those two orbitals are sp2, and they combine to make my sigma CC bond. All right, and I just want to sort of clarify a point here. I haven't drawn the resulting bonding orbital. I'm drawing the constituent atomic orbitals so that you can see them. If I were to draw the bonding orbital, it would be very similar to the other sigma bonds that we've looked at, okay? But we're going to put the atomic orbitals in so you can see what's donating what. And so the CH sigma bonds, we've seen these before in methane. So remember, we used the CsP3 orbital plus an H1s. We combine them so that we could get a sigma bond. Same thing here. So I'm not going to redraw them in the interest of keeping things uncluttered. Okay. The only difference is that I'm bringing in an sp2 carbon orbital as opposed to an sp3 one. Okay, but otherwise they look qualitatively the same. They're still sigma bonds, and the interaction is nearly identical. What we need to do is then deal with this pi bond. Okay, and so I used two of my 2p orbitals in hybridization with the 2s. And so the only thing I have left on carbon that I can use to think about bonding are going to be the last final 2p orbitals. And so I will draw them here. Okay, so those are the 2p orbitals that come from each carbon. And the important points are that that last 2p orbital is perpendicular to the plane defined by the carbons and hydrogens. Okay, so we have a special term for that in chemistry. We call that orthogonal, and the orthogonality really refers to the way in which that 2p orbital can interact with any of the other orbitals in the system. And if you consider the change in sign of the 2p orbital of the carbon on the right and think about that maybe overlapping with sigma with the CsP2 orbital that I've drawn, you can see that part of that will be overlap of the same sign, and the other part will be overlap of a different sign, and the net overlap is 0. And so in mathematical terms, it means that there's no interaction. For our purposes, that 2p orbital is perpendicular. It means that it's perpendicular, okay? The other thing that I want to note here is that the pi bond is formed by overlap of 2p orbitals. The overlap of those orbitals is different than what we've seen before. So when we saw the sigma bonds, it was CsP3 going head on with the H1s. And now with these two p orbitals, what we're actually getting is a side-on interaction. So
Wait, so do the two orbitals overlap? Like, are they like side by side and they overlap?
they
Or-
do, yeah. So I haven't drawn, so I'm just drawing the, things aren't quite to scale and where they should be. I haven't drawn the MOs, I'm drawing the constituent AOs. So those are the two Ps, and they're, in fact, yes, they overlap. They're just a little bit further, sort of for clarity here. Yeah.
Which are the
I'll draw the bonding MOs in a second. Is there another question?
yeah, so are the things that are drawn, are those like I'm just kind of confused as to which are the MOs and which are the AOs in the drawing?
Yeah. So the everything on this drawing are the AOs. Okay. When I write pi here, I'm referring to the bond that is derived from those two AOs. Okay. Does that answer your question? Okay. All right. So the two p orbitals overlap side on. Okay. And intuitively, you might reason that that type of overlap would be less effective than head on. Okay, and in fact, you can see that in this, in my misproportion diagram. It's not all wrong because, in fact, yeah, those orbitals are further from each other, and it's harder for them to interact, though they still do, of course. And so this side-on interaction is still effective, but less significant. So the bonds wind up, pi bonds are weaker than sigma, okay? So a CC sigma bond is on the order of about 85-ish kcals per mole. A CC pi bond, just the second bond, of course, we always in practice, a double bond has two bonds, but we can separate out the pi bond. That interaction is about 65 kcals per mole. So it's about 20 kcals per mole less stable than a sigma bond, okay? And that derives from this less ideal orbital overlap. I'm just kind of, bumping on the side as opposed to ramming the two orbitals together, okay? And it's a general truism because of that difference in bond energy of about 20 kcals per mole. It's a general truism that a reaction that takes a sigma bond to a reaction that takes a pi bond to a sigma bond is typically going to be thermodynamically favorable, okay? And when we start doing alkene addition reactions, that's all we're going to see are transformations of pi bonds to sigma bonds, because that gives us stronger bonds, more stable system. Delta G is negative, okay? So there are, of course, exceptions to this, so I'll qualify it with generally. Okay, so generally pi to sigma is going to be a favorable process, all right? So now we got to generate the bonding diagram. And hopefully what comes out of this bonding diagram will tie back into some of the points that I've just hit on. So we're going to do it here. I'm going to attempt to rotate this. Let me see if that works, because that would make it life a little easier. Okay. All right. Hopefully that doesn't cause any problems on your end. All right, so we're going to make the bonding diagram. It's going to be complicated. I'm just going to say that right there, okay? Get it out on the table. We're going to start with our carbon atoms, all right? And the first step when you're constructing these bonding diagrams is identify the constituent atomic orbitals, okay? We already did a bit of that on the last slide, because we said that the carbons are sp2 hybridized. So I have 3 CsP2 orbitals and 1 2p orbital. Okay, so I'm going to draw them. And first I'm going to, here's what I'm going to do. I'm going to try and draw this on the bottom. Maybe I'll try and fit it all on the top and then use the bottom for kind of like notes. I'm going to draw the 3 sp2 orbitals. Okay, so y-axis is energy as always. Okay, so there are my 3 carbon sp2 orbitals. They're at the same vertical position because they're all identical in energy. Okay, then I got to pencil in the 2p orbital. And the question is, where does that 2p orbital go relative to the sp2? Okay, and to answer that, you want to think about sort of what's in these hybrid orbitals. So what's in the sp2 orbital, that sp2 orbital is 33% s, right? And so we know that s orbitals are spherical. They tend to have an electronic distribution closer to the nucleus. And so while the sp2 orbitals don't look exactly like a 2s orbital, they have some of that character. So they're a bit tighter than a 2p orbital. They're a bit more closer to the nucleus. Electrons are more stable in those orbitals. And so the unhybridized 2p orbital will be slightly higher in energy. So okay. All right, so we established that. That's great. Now I need to put my hydrogens in, okay? And this is, the diagram is going to get a little hairy here. So the hydrogens are donating a 1s. All the carbon orbitals are from the number 2 shell. 1s, very stable, so they're going to be lower in energy than the CsP2. There are 2 hydrogens attached to each carbon. So I'm going to put those hydrogens on either side here. Okay, like that. And it's good. We're making progress. So then the next step is going to be to identify the electrons in each atomic orbital. And the carbons, of course, have 4 electrons. So there's going to be 1 electron in each orbital. And the hydrogens bring 1 electron to the table. Okay. So now we can start the mixing. And what I'd like to do first is combine the carbons and the hydrogens, because then we can see what's left. And that's kind of the new stuff. Okay. And we're familiar with making a CH sigma bond. Okay. And so we can do that on the left. We add 2 of those orbitals and we get sigma CH. Okay. And if we subtract those 2 orbitals, we get sigma star CH. Okay. And then we can populate. So I'm drawing 2 of the 2p orbitals from carbon. So I'm going to have 4 electrons total, and I just fill my bonding orbitals. And then we can do, I'm going to do the same thing over on the right here. So And these are, of course, identical in energy to what I drew on the left. So the vertical position should be the same. Okay, so same thing. 4 half-filled orbitals in, total 4 electrons. I can nicely populate my bonding orbitals. My anti-bonding orbitals are full or empty. Everybody's happy, okay? If any of that's unclear, please review the methane orbital that's in, I think that's in the office hours, in the bonding orbitals in methane where we did sp3 plus H, and that's been recorded. Still unclear after that. Let's meet in office hours, okay? So what I've done is gotten, I've made use of 2 of my carbon sp2 orbitals and my H1s orbitals, so I can just check all this off. You don't have to think about them anymore, okay? And then what's left are the sp2 and the C2p, and if you look back at the previous slide when we talked about the bonding, we said that there was a carbon C2p that made the sigma orbital and a carbon 2p that contributed to the pi orbital. So everything is kind of on track here, okay? And so what I need to do is, first I'm going to take care of the sp2s because that's a sigma bond and we're more comfortable with that. So we're going to do the same thing we did with the hydrogens, okay? No difference, except that the only difference is that the AOs going in are different, but the procedure is identical. So we can add them. And that's going to give me a bonding orbital. And sorry, this is just one orbital. I can subtract them and I get to my sigma star, okay? And so each carbon donates 1 electron, so just populate, good to go. Nothing in the antibonding orbitals, life is good, okay? So now we're down to the final pair, and that's this C2p orbital, okay? And so 2p orbitals pointing up and down, perpendicular to the plane of the carbon defined by the carbons and hydrogens, okay? And as someone asked on the last 1 or 2 slides ago, it's like, yeah, they aren't overlapping, and it's like, yeah, you're kind of right. Like they don't overlap that well. They do overlap, but it's side on, and it's not as good as this, okay? So like this is not as good as this, okay? And so I'm going to have them overlap, but I'm going to be very deliberate about where I place my bonding orbital. And I'm going to place that higher in energy than the sigma CC orbital. So okay, so simply put, there's less efficient orbital overlap, all right? And, this is something that's kind of second nature to myself and Maddie and Zeke and, practicing chemists, but you may seem a little foreign. Anytime you increase the overlap of the atomic orbitals, that's going to be more stabilizing. Rule of thumb, the more overlap, the better, okay? And so pi orbitals, you don't get as much stabilization when you make those bonds, all right? In the same way, and I'm going to draw the pi orbitals on the next slide because it's getting a little busy here. In the same way that we add 2p to make the bonding orbital, we subtract to make the anti-bonding orbital. And I'm not going to say too much about this, but it is also the case that pi star CC is not as high in energy as sigma star CC for the same reasons. the orbital overlap is not as good. If you do have to put electrons in there, they aren't interacting as much. There's less destabilization, okay? But we don't need to spend a lot of time on that. So I can draw my arrows. Let me just do something different here. So I'm going to draw green for the 2p. And then
Wait, I'm a bit confused. So is
Go ahead.
the pi bond or the sigma bond higher in energy?
So I think we're conflating two terms, okay? So when I say it's higher in energy, okay, the orbital itself is higher in energy. If you put an electron in that orbital, it's got more energy in a pi bond than it does in a sigma bond, okay? But the flip side, okay, the other way to think about that is that the pi bond, or sorry, the sigma bond is stronger, okay? You get, when I move electrons from up here to down here, I get more back in terms of energy. Okay.
And that's just because of the overlap you mentioned.
Yeah, the
Okay.
overlap is better. They're more stable. Everybody's happier. Yeah, yeah. So weaker bonds correspond to higher energy orbitals. It's kind of backwards from what, yeah, but weaker bonds, higher energy orbitals. Okay, so then I'm just going to populate.
Sorry, Professor, is there
Yeah.
a reason that you're drawing the pi CC bond at the same energy level as the hydrogen one?
No.
That's just
Yeah, not equivalent. In fact, lower in energy than the 1s. Let me just move that. Yeah. Yeah. Okay. And the deltas, please don't interpret any sort of like absolute deltas from this graph in terms of like, oh, the gap between H1s and pi CC looks like it's bigger than, you know, pi CC and sigma CC, not trying to imply anything. The only relative things that you should remember, you may want to write this down. So what energetic differences are important from this diagram and that you want to be able to get right, like on an exam. So 2p is higher in energy than sp2. H1s is lower in energy than either of those. So that's how we rank our atomic orbitals. And the H1s, you know, lowest in energy because it's in the first shell. The CsP2 better than 2p because it has some s character. The electrons are closer to the nucleus, okay? And then sigma CC is going to be lower in energy than pi CC. Another way to say that, the sigma bond is more stable than the pi bond, okay? And then the same is true, you know, in the antibonding sense. So sigma star CC is higher in energy than pi star CC, okay? Okay, that's all I want to say about that. So those are the orbitals, and we've used up all of our electrons. Everything is good. Copacetic, no electrons in antibonding orbitals. The molecule is happy. You have ethylene. Okay, so let me show you what these orbitals look like. Yeah.
Do we have to worry about like the difference in energy between the sigma bond between carbon and hydrogen and the sigma bond between carbon and carbon?
So in practice, the sigma CH bonds are a little bit stronger. Okay, so these should be moved down, but it's not something that is going to make material difference for us. You know, there's not, just because there's not many cases where you're comparing like a CH bond to a CC bond. You will, for example, compare different CH bonds, you know, so when we get to alkynes, we'll see that CH bond is very stable, much more stable than an alkyne, than a CH bond derived from an alkene or an alkane. Yeah, basically, you want to be able to think about sort of relative stabilities of a certain type of bond. Comparing those, at least for carbon and hydrogen, we don't really, you know, those comparisons aren't made that frequent. Okay. All right. So
Professor, quick question.
Yeah.
Could you write out like the relative energies? I'm just having a bit of trouble like following the verbal explanation.
Okay. So, yeah, let me think about, maybe I'm going to do this on the next slide. Okay.
Okay, no worries. Thank you so
Yeah.
much.
Yeah. Just because that was getting busy. So relative energies. Okay. And so at the very bottom, okay, okay, at the very bottom, I'm going to have sigma CH. Okay. And then somewhere above that, again, it's going to vary. So I don't want to give you guys numbers, but it'll be 20 to 30 kcals. Somewhere above that, I'm going to have sigma CC. Okay. And then somewhere above that, I'm going to have pi CC. Okay. And then if we go into the anti-bonding space, the trend is reversed. And so progressing up, I've got no more bonding orbitals. So now I'm at pi star. So I'm up here. That's going to be my lowest energy anti-bonding orbital. Sigma CC on top of that, or sorry, sigma star, and then sigma star CH on top of that. Does that help, Caroline?
Yeah, that's very helpful. And just to ask like a bit conceptually, is the reason then why like the bond, like the pi bond is like so easy to be broken is because like the difference in energy between the pi and the pi star bond like is a lot less than like the difference in energy between a sigma and a sigma star bond or a sigma CH and a sigma star CH bond.
Yeah, exactly. So it's exactly right. So a bond is stable. If I want to break that bond, I need to put energy into the system equal to the bonding energy, right? And so if that bond is weaker, it requires less energy to break it. And so the pi bond being the weakest is what goes first. Yeah.
Okay, thank you very much.
We actually have a certain so this is a very important point, and it's a very important because in fact these are the orbitals that we think about the most with alkenes. Okay, and again, the reason being the reason is exactly what Caroline explained. So the electrons in the pi bonding orbital are high in energy. It's the weakest bond. It's easiest to break that bond and do something to those electrons, okay? And if I need to add more electrons, which we sometimes do, less common, pi star is the lowest energy place that they can go, okay? So maybe you can think about it as like, I don't know how dorm room selection works, but suppose they were like, okay, first come, first serve. And it's like, they were very different. And then, you're first and you say, okay, I want the 5-bedroom suite with the pool and the sauna and, and room service. Okay. That's sigma CH. All right. The next one would be like, all right, you're going to get 2-bedroom suite and, you have to share a bathroom. That's sigma CC. Okay. Pi CC is going to be, you're bunking in the cafeteria. We'll hang up a curtain. Okay. And so who wants to get out of there the most, right? Pi CC, right? Pi CC is going to be the happiest to depart. Okay. And so we have a special name for these that we call these the frontier orbitals. You don't need to know this, but Pi CC is a frontier orbital. Pi star is a frontier orbital. They're the ones that are most energetically accessible in the system. All right. All right. I got to keep going here. Just very quickly, what do these look like? And again, I'd sort of I'd encourage you to take a look at your book for a better drawing. But if I wanted to draw pi CC, it would be something like this. So I can draw my carbons, my hydrogens. And then if I wanted to draw pi star, it would look something like this. And again, please don't hold me accountable for my drawings. Okay. And so, you know, different bond, but they play by the same rules as the sigma bond. So we said the bonding orbital in a sigma bond has a bonding interaction between the atoms. We can see that for pi CC, I got the same sign as I move between those two atoms. The sign is different on either side, but you still have a bonding interaction between them, okay? Pi star CC, antibonding orbital. We said antibonding orbitals are defined by the presence of a node between the two atoms of interest. You can see that there is no bonding interaction between the two carbon atoms in the antibonding orbital. There's a change in sign of the wave function that leads to that antibonding interaction. Okay, so let me just you know, I'll stop there because the next topic is sort of stereoisomers of alkenes, and we could try and ram something in here, but we'll take a break there, and I'll hang around as I do for office hours. Again, we had a problem like this on your Friday problem set where we asked you to, you know, construct a bonding orbital for a CN bond. Okay, this is very important stuff. We really want you to know it. If it's unclear, let's get some help, and we'll try and fix it up. Okay. All right. I'm going to take a brief break, and then I'll be back in about 2 or 3 minutes.